So today we're going to look at heating and cooling, which you might remember as being the topic we were all on when the school had to close the first time and we had to move off and do things remotely. And we're going to look at this idea of heating and cooling, which is okay because we've just looked at temperature. We just looked at the generation of the Kelvin scale and the relationship between temperature in Kelvin and the kinetic energy of the particles in them. And this is quite nice for things getting hotter or colder because there is a law in physics. Several laws in physics, but one of them is called the second law of thermodynamics, and it states that the following: thermal energy will naturally move or naturally flow from hot objects. I'm going to use red, even though I shouldn't, because as we know from stars, blue is hotter than red, but people seem to know this because of water and so on. From hot objects, where there's a high temperature, to cold ones. Okay, so energy flows from high temperatures to low temperatures. If you want to break that, so you want to build a fridge or a freezer and make the energy go the other way, well, to do that you need to put energy in, and that's why fridges and things have motors and various refrigeration units at the back. That's why if you feel sort of the back around a fridge or a freezer, it'll actually feel quite warm. But it explains so many things. It's why we get energy from the sun. The sun gives off energy because it's really, really hot, space is really cold. We get some of that energy. It's why the cup of tea that you make at the start of these little videos is cold by the time you've come back to it, because my videos have captured your imagination for a whole 30 minutes. Now, your tea will cool down to the room temperature. It's also why you need, why humans, because we're a sort of a, we're an equatorial sort of animal that's moved out sort of north. It's why we need to wear jumpers and things when it's cold, because otherwise we lose too much energy too quickly and our body can't replace it. You like your body core temperature to be about 38 degrees, but the air around you is not 38 degrees. So you need to, part of your entire respiratory output is in order to keep yourself warm, because otherwise you'll keep losing that thermal energy. So this is a natural law. This is a natural process that happens. Things do not spontaneously gain, suddenly drop in temperature. I know there's a few tricky things in chemistry with some of their sort of is it endothermic experiments, but there's deeper reasons for why those things happen. It's not a spontaneous kind of like, ooh. So yeah, now what we're going to look at, and I've got several demonstrations in the lab, are basically there are three methods in which this happens. Okay, so there are three methods of heat transfer, and they are conduction, convection, and finally radiation. Okay, and so I'm going to very quickly summarize them, and then you can sort of see them in action. Okay, now there is actually, you can argue there's also evaporation, which is when you lose energy by something changing state. So if you boil water, like the steam coming off, but we tend not to worry about that in this particular test. So what are they? Conduction happens in solids. If you hold a solid and you stick one end, if you hold a metal pole, stick one end into a fire, eventually the other pole will get hot and you'll burn yourself. And this happens due to the vibrations of particles bouncing things along. So conduction occurs in solids. Okay, and the way that happens is that particles that gain energy are hotter, vibrate more, and pass the vibrations along. Okay, so if you've got a row of, remember that in a solid you've got sort of it nicely organized in a nice sort of regimented fashion. If I sort of heat this particle, then it's going to vibrate more, left and right, left and right. It's going to therefore bounce into its neighbors, which means that one's going to vibrate, and then that's going to bounce more, and this one will gain energy, and this one will gain energy, and slowly and slowly, so you pass the energy along. So if you add sort of energy there, it'll eventually get all the way sort of along via vibrations. Now, so basically, this is what happens in solids. Okay, so conduction is a thing that occurs in solids, and what you probably already know is that you've got metals are good conductors, and plastics are poor conductors. Okay, so then we often use the term insulator as a bit of a catch-all for things that are poor conductors. Metals are good conductors because they've got free electrons that can zip in and around and spread energy around. But yeah, essentially, that's actually all you need to really know about conduction the time being, because you'll see a few examples of it, but it's often about like how we change the rate of it. Second one is convection. Okay, what's going on in convection? Convection is what happens in fluids, and by fluids I mean liquids or gases. And fluids are things where the particles are free to move over each other, not in a fixed position. And what will happen there is that as things gain energy, whatever it is, air gains energy, particles spread out, which if you were going to imagine a load of particles, if I suddenly got these particles start moving loads, then they're going to take up more space. They become less dense and they rise. And what will happen is they rise and they travel around, they'll bump into things, they slowly lose their energy, so they cool, they become more dense, they sink, and you end up with a thing called a convection current. So we're going to summarize that exceptionally quickly. So convection occurs in liquids and gases. The particles in the gas gain energy and spread out. The gas becomes more dense, less dense. And rises. It is replaced by colder, denser, and I'm going to have to quickly just go denser gas. And so it sets the cycle. And it's called a convection current. So conduction, solids, convection, liquids and gases. Final one, radiation. Radiation, remember the EM spectrum and that lovely song, infrared radiation. Right, this, no particles involved at all, so this could happen through a vacuum because these are waves of energy. So radiation, is emitted as waves. Well, can't spell. It's not the best sentence I've ever written, this one. As waves of energy, often infrared, is what we feel. It's most things we come across, they're emitting infrared radiation due to their temperature. Yeah, that's funny. So that, and can travel through a vacuum. And what's important about radiation is that we can control the amount of radiation by controlling the color of things. So different colors some colors are really good absorbers and emitters of radiation, and some are very poor. And that is to do with their color. So dark matte objects, so dark as a dull object, so for example the background that I've got here, that is a good absorber and a good emitter of radiation. So dark matte, so sort of not shiny colors are good absorbers and emitters of radiation. Light and shiny colours, so white, silver, are poor. Emitters and absorbers. Radiation. Now, at the moment, that's all I want you to know, because I'm now going to show you the second video, which is basically about this, where you're going to see lots of several examples of these different ones. So the idea, just to summarize, conduction, solids, vibrations of particles bouncing it along. Convection is about liquids and gases, where the particles are moving around because of changes in density. Radiation, well, that's just waves of energy that will come from anything that's hot, and we can basically try and control it by the color that we select. And these things are all going to come together when we try and think about how we insulate. But that is kind of the underlying physics. It's time to now watch some demonstrations.